Okay, so this video is all about the factors that can affect resistance. So we're going to start off with temperature. Okay, so for example, at the temperature of our wire, we know can change the resistance. So we're going to talk about the reason why behind that. So for example, we're talking about the temperature. We need to really think about the structure of our components or of our metals that are being used. So when we look at our metals, we are made up of a lattice of positive ions with these free electrons to move. And those electrons moving are the current. Remember, resistance is the opposition to current. So the slower it is for those, or harder it is for those electrons to move through, the more resistance there is. So if we talk about increasing the temperature, we're essentially going to be giving these ions more kinetic energy. So these ions are going to be vibrating, and they're going to be vibrating more and more and more. Now, if they're vibrating more, it's going to be harder for those electrons to pass through because they're more likely to collide with them. Okay, so if these ions are vibrating, it's going to be much more difficult for these electrons to pass on through. So in this case, we say we increase the temperature, the positive ions gain kinetic energy, so they vibrate more. This makes it harder for the electrons to pass. Well, if it's harder for the electrons to pass, the current has decreased, and therefore the resistance has increased. So our increase of temperature can increase our resistance. Okay, so that's the first one. The next one is all about length of wire. So in this case, we're going to talk about how the resistance changes with the length of the wire. So again, thinking about it in terms of those electrons moving. So think about these electrons moving through the length of a wire. Okay, as we go through, what's going to slow them down is colliding with those ions, because they're going to collide and they're going to have to move around. So the longer I make this wire, the more chance it has of colliding with these ions, okay? Whereas if it's only got a short wire, it's only got a short little path, it's got less chance of colliding with the ions. So we can say that if we've got a longer wire, we've got more chance of the electron colliding with the ion, and therefore it's going to slow down the current. Okay, again, if it slows down the current, what that means is it's going to be increasing our resistance. I'm just going to try and move this up a little bit so you can see that. Okay, so a short wire, okay, has less chance of those collisions. Okay, so it's got more chance that the current's going to be increased, and so the resistance is going to be decreased. So the longer the wire, the more chance of collisions, so we're going to slow down the current, so we're going to have a higher resistance. So longer wire, longer resistance, or higher resistance, sorry. Shorter wire, okay, less chance of collision, so a better current, a higher current, and so our resistance is going to be shorter. So we say that resistance is proportional to length. Okay, so the longer the wire, the higher the resistance. The shorter the wire, the smaller the resistance. Okay, our other factor that we could look at is cross-sectional area. Okay, we can talk about cross-sectional area as being our thickness. So if we have a really thin wire, you can also think of it sometimes like a straw or like a little tap maybe, and letting something flow through. If we had a really small kind of area for it to flow through, we've only really got one or two pathways for these electrons to move through. So they're going to kind of get cramped up moving through there. If I make it wider, I'm going to have many more places for those electrons to start flowing through, okay, which means that I can get more of those electrons to flow through there, all right, which essentially means I'm going to be increasing my current because I'm going to have a faster flow of those electrons, all right. So in terms of thickness, okay, larger cross-sectional area means we have more pathways, so it's easier for the electrons to flow through, so the current is going to increase. So in that case, the resistance is going to decrease. So we'd say that if we increase the cross-sectional area, so a thick wire, we're going to have a lower resistance. In the opposite way, a thin wire, so a small cross-sectional area, we're going to have a larger resistance. So in this case, we say resistance is inversely proportional to the cross-sectional area. Okay, inversely proportional means they do the opposite. The last one is a little bit more complicated, and this is also to do with the type of material, okay? So different materials have different atomic structures, they have different lattice formations as well, which basically is affecting the conductivity of it. Now, we actually talk about the resistivity of this, so each individual material has their own resistivity. Now, this is something that we do at the diploma level, and it's given by this equation, which is resistance is area divided by length. Okay, so we also have to take into consideration not just the resistance and the resistivity we calculate for different materials by the resistance at a given temperature, the area and the length. So they've done all these different experiments on different types of materials to give a value for resistivity, which you can think of as like conductivity, but that is kind of slightly incorrect, but it's a nice way to think of it for grade 9 at least. So basically it just means the type of material. So different materials have different resistivities. You don't need to know this equation, you don't need to know the word resistivity, but as long as you know that different types of materials have different conductivities because they've got different structures. Okay, so we could also think of it in that way to make it a little bit easier. So those are the factors that affect resistance.